Let's start by looking at deterministic methods. We have deterministic methods, and we'll start by looking at deterministic methods that create continuous surfaces from irregular or regularly measured point values. So these are locations, points in space at which we measure the value of some variable. And they are irregularly spaced, so they're not equidistant from each other. They could be randomly distributed and spaced, or they could be systematically even. So they are regular distances from each other, and we just want a finer scale representation. So deterministic methods, what distinguishes them from optimal geostatistical methods is that they assume a model of spatial autocorrelation exists within the unmeasured locations from the measured values, basically. And these type of ones are inverse distance weighted, global polynomial, local polynomial, or radial basis functions are common ones. The most common being, of course, the inverse distance weighted, which is what we'll look at first. Now, just to understand a little bit of spatial autocorrelation here, let's look at one. So this panel right here. And you'll see that it has a location A and B. And overall, there is spatial structure here in one. Spatial structure meaning that we see high values here and lower values over here. And there's a smooth gradation of color that follows a smooth gradation of values from the high areas to the low areas. Now, if we were to take a fixed length of transect between A and B right here, and we looked at a cross section, so that means just like cutting, if this was a, remember this is a three-dimensional thing that we're just representing in 2 dimensions here. It's basically a hill. And if we were to slice that hill with a cake knife, let's say, and along this dimension here, and we just look at the values between A and B, that's called a transect. And that's plotted up here. So up top here we have distance, and that's distance between A to B, right there. So that's just measuring the distance between A and B. And then the Z value on the y-axis, which represents the height of the hill. So how high is it here, 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 etc., all along that line. So what would it look like then? And that would be the cross section. So if we look at that, it looks like this. So this wasn't a hill, it was a valley. So those are actually, by seeing the cross section, I can see that that's low values to high values at the corners and the edges, you know. So it wasn't a hill, but rather the inverse of a hill. In this case, a indentation of some kind. And from A, the values, the cross section, and the height values are low, and then they get higher as we get to B. And so the cross section looks like that. And notice the cross section it looks like a smooth differentiable function at any point or location. Right? There's no break in slope anywhere. So we could find the first derivative of that function once we find the type of function it is at any location. Now, in the same space, we have B, or number 2 over here on the right-hand side. So again, this is in the same location, same space, but has very different distributions of values. And in fact, the values in 1 and the values in 2 are identical. But they're just arranged differently in space. So that if we now look at the same transect from A to B, and we look up here at the graph, that's what it looks like. It's just showing random variation between A and B. Sometimes it goes up and then it goes right down, up and down, up and down, up and down, quite frequently. So over that same scale, which is the length of that line, A to B, transect, we have very little predictability. So there's no predictability that if you take one location, that the next location will be higher or lower necessarily. Only at very small scales is the predictability there. So that if you take a very small location or range here, then you know that around that range or around that location there, that very small distance, d, that there would be similarity in the values surrounding that specific distance. But over the range a to b, it's unpredictable, so it's very unstructured. That's another way to say that. And that's very different from the structured version on the left. And so the one on the right exhibits no spatial autocorrelation, whereas the one on the left exhibits spatial autocorrelation. And that's called a random field, another name for that. And we can see that visually, and spatial autocorrelation can show us that that's true. But if we did anything, if we looked at any of the other type of statistics for these two data sets that weren't spatial, like the mean, the variance, the variability, the standard deviation, they would be identical between 1 and 2. There's no way to tell or distinguish between 1 and 2 just on a basic descriptive statistical measure. So it's the spatial autocorrelation is fundamental here. To model spatial autocorrelation, we can measure a straight line distance from any given point in geographic space and plot that distance on a graph. So let's say here on this graph on the left, we have a location. Our location right here is the location where we want to estimate. So we want to estimate a value that's at that location, and we have no measured values at that location. So we're working in a data set where we have no measured values at this location on the graph. And this is a one-dimensional example, obviously, just to make it easy to understand. And we want to figure out, okay, what is a value there based on values that are surrounding this location in space, where the location in space is the distance on the x-coordinate. So we can say, okay, between 1 all the way to 5, we say, okay, well, this is how the distance affects the decay of influence of other values from that location. And at the location, we have 1 up here on the y-axis. 1 is the relative weight. So that if there is a measured value at this location on the x-axis, then it would have a very high weight in influencing what this value should be right here at that yellow gold point. Whereas if we move, let's say, over here to distance 2 away from the location we want to estimate, then the relative weight would be that, 0.5. So if we had a value here that we observed within this space, so we have a numeric value, maybe it's 2.2, for example. Well, it would be 2.2 times 0.5 would be the weight that it would influence in the estimate going here, because it's further away. And this curve here at the top, the black curve that's concave up, is the assumed model of spatial autocorrelation. So we have that assumed model, and then we can use that to derive weights to get how much something should be weighted according to how far it is from the location at which we want to estimate a value. Obviously, if you went to 3 units away, you'd be at around 0.3, let's say. And as we get further away, like all the way up to 5 units away here, and this can go on infinitely, let's say. This curve here could go on, forever, just getting smaller and smaller and smaller, approaching 0. So at 5 units away, the weight would be, maybe around 0. 2. So values here would be multiplied by 0.2. Values here would be multiplied by 0.3. Any values over here would be multiplied by 0.5. And if we had those three values measured, let's say 2.2, let's say that's 5, and this is 7, well, it would be 7 times 0.2, 5 times 0.3, and 2.2 times, what is it here, 0.5. And we'd add all those together and divide it all by the sum of the weights, which would be 0.5 plus 0.3 plus 0.2, and that value, whatever it is, let's say that's approximately, it's equal to 3.1, that would be assigned to this unknown location, and that would be called an interpolation, and that would be an inverse distance weighted interpolation, because as distance increases, the weight of influence of existing measured values on the unknown location decreases. We'll see an example of that, a full example of that in the coming slide. That's just to give you an idea of how weights work, so spatial weights, depending on distance and an assumed model of spatial autocorrelation. So inverse distance decay or inverse distance methods are based on this model here of change of value with distance. And they're pretty straightforward. It's just a weighted average of the values that have been measured around the value to be estimated times the weight that are associated with each of the values, and the weight comes from this equation here. So for example, if I had a known value that was 20 meters away from the location I want to estimate or interpolate at, then its weight would be about that. It would have this much of an influence of, that's about 0.05. So it would have approximately 0.05 times the value of the known sample equals the, or will contribute to, we'll say approximately equals the new value, new interpolated value. Like so. So it's each value times the weight divided by the sum of the weights. So that's called a weighted mean, basically. And the weights, again, come from inverse distance. And notice this is inverse distance to the power of 1. And that just means that it's inverse distance, because that power can change to 2, 3, 4. And the more the power changes, or the higher it gets, the more steep these things become. And we'll see an example of that in a couple seconds. Easier than that than to draw it on there. So again, there's a distance of 20. So this is assuming your point or location to be interpolated is 20 meters, let's say, away from a known sample location, a sample with a value. And there the weight is, in this case, 0.05. So some geographic phenomena will vary smoothly and regularly or continuously over space. So for example, for something that is continuous over space, you could have a weight like this, 1 over d to the 0, and of course any value to the power of 0 is just equal to 1, and so that whole thing equals 1. And that means there's no change with distance. So any value, no matter how far away it is, like 20 meters, 60, 100 meters or units, whatever they might be, it'll have equal weight on the unknown value to be estimated. Here we have a inverse distance weighting that is between 0 and 1 for the exponent of distance in the denominator. And here you can see that, well, at, let's say, 20 units, you'd have a weight of approximately 0.4. So the sample value when predicting a location 20 meters away, would have 0.4 times the sample value in terms of its influence. So it would be 0.4 times that sample value, 0.4 times another sample value if it's 20 meters away. And likewise for 40, it would be slightly lower than 0.4, maybe 0.39, etc. This is the black curve, that's inverse distance. So that's just 1 over distance to the power of 1. And here's a stronger decrease in weight with increasing distance. And you can see that difference again, we know that's already going to be 0.05 right here as a weight. And that's very different from up here when we have 1 over to the power of distance to the fourth root, or 0.025, where that's going to be 0.4 approximately for that same. So you can see here that the way of the amount of influence that a sample location has at an location to be estimated is much larger for smaller values of distance, of the distance to the power, smaller values of the power to which distance is raised in the denominator. And this is inverse distance squared. In this case, at 20 units, you have almost 0 as a weight, approximately. So only values very close to the location that has to be estimated will have any influence on that local value. So it becomes more and more localized, more and more local as you increase the power to which you raise distance to in the denominator. And most packages or software and most people will just take inverse distance squared as the most commonly one used, although there's no reason for it. That's the problem. You have to have some reason to use a particular distance exponent. It has to have something to do with how you hypothesize your values change in space, change with distance as a function of distance in terms of their weight on interpolated locations. And if you don't have some reason or justification for that, then you're just choosing an arbitrary value. And that's all right to start with, just to have a look, because there's no hypothesis being tested here. So you can try inverse distance squared, etc., just to see the influences of these things. Here we have a region, and we have 1, 2, 3, 4, 5 measured values in there, which are the blue dots. So each blue dot is a measurement, and this is an irregular lattice. Of measured locations. Irregular meaning that the locations at which we have measured values aren't regularly distributed. So if they were regularly distributed, we'd have a blue dot here. We're going to make that a different blue. Blue here, 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 etc. So that would be a regular lattice. Now, what we've done is, on top of the irregular lattice of existing measured locations and their values, we've imposed a regular lattice, shown here by the dotted lines. Each dotted line where they cross is a cell center. And at each cell center, we want to estimate the value that might be there based on the known values. And the red dot here is showing one cell center example. And it's saying question mark. Well, what do we want to, in other words, what is this going to be in terms of a value at this red dot? And of course, keep in mind that where that red dot is, the red dot moves to each subsequent location like this, until all locations in the regular lattice have an estimated value. So we'll just do this example for one location here. So first we measure the distance away from each of the measured values to the red dot. So for example, these two are at a distance of 1.41 units. Then we draw an inverse distance weight. So this is your weight right here, 1 over d, like so, or d squared. It's 1 over distance to the power of something. Then we say, okay, at distance 1.41, what is the weight going to be? In other words, how much influence is this location and this location going to have on the unestimated value here, or the value we want to estimate in its location? So we draw a line from 1.41 to where it intersects our inverse distance curve here, and it intersects it there, and we then read off the value at that location on the y-axis, which is weight. And here it's 0.0503. So the weights then, we can just assign a weight to each of those distances instead, transform them into the weight, like that, and then we can multiply that weight times this right here, plus that weight times this value here. And at the bottom of the equation, we just put the sum of the weights, 0.503 plus 0.503, right? So, and we did those two at a time, these two simultaneously, simply because they have the same distance away, and that's what matters. We need to get a weight for each distance. So let's look at the next one. There's 105, and that's a distance unit of 1 away. So again, we draw our inverse distance curve. We'd find that where the value of 1 is, and it says the weight of 1 equals 1. So 1 times 105. And then at the bottom, we add to our rolling total of the weights, the value 1 for that weight. Let's look at the next one then. So distance 2.24. So at a distance of 2.24, what will the weight be? Well, we draw our inverse distance weighted line or curve, and we mark off 2.24 on the x-axis and find the weight, which is 0.199. And we multiply that by 100. And that goes up here in the numerator. And then again, we add the 0.199 to the denominator as part of the rolling total of the weights. Finally, we have one more left, which is the furthest one away. And so it should have the smallest influence. So it's at a distance of 4.24 units away. So we draw our inverse distance curve and mark off the distance of 4.24 on the x-axis and find what the y value is for that location on the x-axis where it intersects the curve. And it has a weight of 0.056. So then it's going to be that value times this value. We add it up here. So it has a very little influence at 4.24 distance units away. Even though it's a large value, it has a very small influence on what this value over here would be. And that makes sense from a spatial autocorrelation perspective, right? Because it's furthest away, it should be more different than things that are closer, such as 105, which is only 1 unit away. It had a weight of 1, and this one has a smaller weight. And of course, we add the 0.56 here to the rolling total, and we then have our complete set of numbers to estimate this value here, and it's 107.95. So the estimated value based on inverse distance interpolation is 107.95. And this is, again, just 1 over distance to the power of 1. So that's inverse distance. And that process happens for each cell location, or each cell center location in this regular lattice that is overlaid in that space. And notice we're not going outside of the space defined by the minimum and maximum X and Y values of the data set. So here, 1, 5, 1, 5, so column 1, row 5, and then we have over here 5, 5, 1. So the fifth column, or the fifth X value 5, row 1. So we don't extend the estimates outside of that domain, because that's called extrapolation, as you saw earlier. So once we put those and work them out using this equation, right? So we have 100 times 1 over 1.41 squared, 105 times 1 over 1.41 squared. I have 100 times 1 over 2.24 squared. That's just, again, that's how we're getting, right? So it's the distance values here. So if you're not sure how these, like this one is coming in, well, we have, if it's inverse distance squared that we're using, well, then we have 1 time divided by 1.41 squared, which is the distance of that value. So 100 times 1 over 1.41 squared is where we see right here, this case, that's how we get the value of 0.053. That's just 1 over 1.41 squared. So we do that for each of the values. It's just showing here arithmetically, step by step, what's happening. And then remember, we have to divide everything by the sum of just the weights. So we exclude the 100s here, and we put everything else at the bottom. That's how that's coming about there. Sum of the weights. We just work it out. This is just addition, multiplication, and we eventually get this value right here of 107.9451. So under the inverse distance rule that we're using, in this case inverse distance squared, we have 107.95 as the estimated value for that grid cell location. And then we move over to the next one and do the same thing. Inverse distance weights will never produce values that are greater than or less than the input data set minimum and maximum Z values. So you don't end up with any things like what we call peaks or pits between observations. And this is an example on the right-hand side here, where we have a real-world variable. That's the brown line. And this is, again, is a cross-section or transect. Or you could think of it as a one-dimensional example. So the real-world variable is this hill that we see here, and that's a Z value here on the Z-axis. And this is the X-axis, and its distance. And what we see here is we have a real-world variable, and then we have where we have the locations, which are the points, where we have observations. And then the inverse distance weighted approximation is the black line. And what we see here is that between the observations, we have a good estimate following the real world. But if we miss something like getting a sample up here, and we don't have that sample, well, we get then this flat top effect right there, where you just have the same value, going between those two things. So we miss that peak in the real world just because of sampling. Then it follows along fine. Except outside of the range of input values, so the input values again are the circles, the points, we have also mismatch here, and we have extrapolation of values outside the range or the spatial domain of the input irregular point data, or regular point data, whichever, that has the values measured in the real world. And so there's always issues like this. With any interpolation, you got to be careful not to extrapolate. And hopefully you have a sufficient data set to support the majority of or the main form of whatever surface it is you're modeling. In this case here, with this sampling strategy of the 6 samples that we have there, obviously we would miss something like this, a major peak, because it can't be modeled from this. So there's no way for this location to know that it's on a increasing Z. So Z is, you see Z is increasing here. So it's not taking that type of information to know, well, maybe it should increase a little bit more here as well. Likewise, then decreasing. So it doesn't know that, the inverse distance interpolator. So whenever there's a missed peak or pit, it will just, create a straight line in the sense of 2 dimensions. 3 dimensions, it'll create a cline or a surface that just nicely fits between those 2 things linearly. It's a linear interpolator in that sense between points. And so these are things that are drawbacks of inverse distance weighting, for example, in that it doesn't know contextually really what's going on except in its immediate neighborhood. And this is just showing what it would look like with increasing power of D. So where D is less than 1, we would have something that might look like this, where we don't have as many large or very localized bullseyes. But as D gets larger and larger, so the exponent of D from 2 to 3 to 4, etc., we end up getting more of a bullseye effect, where around any sample location, the values will be very similar to that sample location. And that produces the haloing effect we saw in the previous example. Here is just a classified map, whereas the previous example was using a continuous version, so you could really see those bullseyes more clearly. So it's not necessarily a visually pleasing thing, but it does gives us an idea that, okay, we have low values in this area, higher values over here, here, and here, maybe low values over here as well. And we also see values even in places where we have no data, like down here. Again, that's that extrapolation that we have to be careful of when we use any type of interpolation technique, because the values down here are just extrapolated out from the values near the edge. So the values right in this zone here. And so they'll just keep going like that. And those are extrapolated and have very high uncertainty associated with them. Inverse distance weighting is an exact method of interpolation in that the inverse distance weighting function, should a location to be estimated coincide with a location where there is a sample value, then the location to be estimated will just take on the sample value. And that's it. And that makes sense from an inverse distance weighted interpolation perspective and a spatial autocorrelation perspective, in that the value should be what it is where it is measured. Now, it's not very often that you will find a value that has been measured in your sample points that is supporting the interpolation, the irregular lattice. It's not often that you'll find one that coincides with an output regular grid cell or grid cell center. So it doesn't matter too much that it's exact or inexact in that respect. And it will never generate smoothness or account for trends in the data. Unlike methods that are inexact, which can ignore that the idea that something estimated must equal something measured at the same locations when they coincide. Inexact methods can override that because they use the spatial context as well, the mini points around them, to figure out what the general trend is in a particular subregion of the sample space. Also with inverse distance weighting, there's no prediction errors. So you just get a result, which is a prediction, and we don't know the errors. So we don't know what those are, the error terms on those things. I'm just trying to put an E there. So this epsilon for error, we don't know what those are. And it's obviously inappropriate for values that don't decrease or increase over short distances quickly. Because remember, with inverse distance weighting, depending on the power of the exponent, even just inverse distance versus inverse distance versus inverse distance squared, the most common is inverse distance squared that's used, and it rapidly decreases. So you have a very rapid decrease in the weight of influence for locations as they are at a distance from the point to be estimated. And that's very quick. It's a very quick, rapid decrease. And so if your variable isn't the sort that decreases that rapidly in space, inverse distance may not be appropriate for your interpolation. It also assumes that we have an isotropic process. That means that the decay in influence of surrounding values with distance from a point to be estimated is the same in all directions. So an isotropic process means that, inverse distance is the same in all directions. Whereas an anisotropic process, on the other hand, is one in which you can have variable distance decay functions according to the direction from the location to be estimated. So let's say northeast southwest might be inverse distance, but southwest northeast, or southwest, here, let me draw it here. So that might be 1 over distance, but this direction from the point to be estimated here might be 1 over distance squared, because you could have that type of a situation whereby the influence with distance is different as a function of direction. So anisotropic processes. And inverse distance really can't take this into account, since it's just based on a supposed or imposed model of spatial autocorrelation. Undertaking inverse distance weighting in ArcGIS just means going to the Analysis tab and then opening up the Geostatistical Wizard. The Geostatistical Wizard contains the interpolation techniques as part of the Geostatistical Analyst extension. So you may have to go in and, again, load the extension for Geostatistical Analyst if you have not already done so for ArcGIS Pro. Assuming that's done, then you can open the Geostatistical Wizard and you can choose inverse distance weighting. And in our case, we're going to look at Overbrook aesthetics and the field called AVG-INDX, which is the index, the dimensionless index of aesthetic value. In ArcGIS, we have many variants for inverse distance, many options that you can change. So you can increase or decrease the power or optimize the power. Optimizing the power will interpolate a number of surfaces through cross-validation. And we'll talk about what cross-validation is. But basically, cross-validation is, well, it's already talked about later on, but in a short way, cross-validation is a means by which a surface is created, an interpolated surface is created by using n-1 points. And then at the one that was held out in what we call leave one out cross-validation, the one location that was held out, the difference between its value, which is a measured value, an observed value, and the surface that was created without it, are subtracted to get a difference. And you can think of then, if that's done for each point, you make 167 IDW inverse distance weighted interpolations. You have 167 difference values with leave one out cross validation. And optimization means looking at the sum of those errors in various ways to minimize them according to the exponent for inverse distance. So at which exponent are those cross-validation errors minimized? And that would then be the best exponent you could get for inverse distance weighting for your data set. So that's possible here through optimization. You can choose the number of points to be included in each unknown location's estimate. So generally, because points, right, at a distance decrease very quickly with distance, so the relative weight increases very quickly with distance, with inverse distance weighting, we can choose, let's say, only the 15 closest points, which is the default. So the 15 closest points to use in the estimation of the unknown location values, the interpolation or the regular lattice values. And that's usually fine, 15, 20. Here, for example, we have a fairly a somewhat regular distribution of values. So we could choose all of them, for example, or 120 of them or whatever, or just 20 of them or 15. And the idea is that when you choose 15 versus all of them, it doesn't make a big difference, because with all of them, all those other ones have such negligible contributions to the estimated value because they're so far away. And the other thing it allows in the geostatistical wizard is the idea of trying to integrate some anisotropy in the process, in that weights can be directional according to sectors of a pie, So you can have sectors like that. So that's 1, 2, 3, 4. You could use one aspect, one distance weighting here, another here, another here, another here, for example. So, but there's no rigorous way to figure out what those should be in this context. So our data that we'll use in the example is for Overbrook. Overbrook is a neighborhood just across the Rideau River from Sandy Hill. It's a neighborhood that contains both low-income areas, residential areas, and very high-income residential areas. It's been undergoing active gentrification for a number of years now, for the past, well, it's pretty much almost finished, but at least for the past decade and a half, it's gone intense gentrification, starting from the Rideau River, which is right here. That's the Rideau River region, and moving inwards. And then from Saint Laurent Boulevard, moving inwards. And so we have various pockets in here of low versus high income regions, socioeconomically speaking. And the idea then is we might have variability in the aesthetics according to those socioeconomic levels that we find in there. And so the locations here are based on a direct observation, an observational checklist or instrument, whereby students go out I trained 2 students to go out into the neighborhood, and at each block to assess the neighborhood for aesthetics. And this is things such as the upkeep of lawns, the degree of flowers and shrubs, the upkeep of the homes, and this type of stuff. There's a lot of things in that checklist, and from that we made this index, which ranges from 0, possibly 0 to 5, or 1 to 5, I should say, where 5 would be the best and 1 would be the worst. And so the values you're seeing then are index average, or the index values. So they go up to like 3.32, and you can see they're kind of high near all these ones over here, very high, and the 3.7, and then you have just across the Vanier Parkway here areas which are in the 2s. A lot of 2 areas here, 2s, and then there's some 3s and 2.5s, and then some more 3 pockets up here that reflect the ongoing gentrification in that particular neighborhood. And so we want to make an estimate, just a continuous surface estimate, so we can better visualize these numbers, basically. Because it's hard to just look at the numbers and say what's going on where, because it's easy to miss a number. So we could have local pockets of opposite things that are happening that we just don't see when we look at it visually like this. So an interpolation will help us. Now, a large part of the neighborhood has no observations. This is where the baseball diamond is, and there's a hotel here. baseball, stadium here, and then some government thing over here. There's Canadian Tire, Best Buy, and stuff like that. No people live there, but it's still part of that neighborhood boundary. So we're going to end up with extrapolation in these areas for sure. So we have to know ahead of time that yes, we'll get estimates everywhere in this region, but they mean nothing because we have no data to support them. As I mentioned to start, make sure that you go to your settings, licensing, and make sure that you have geostatistical analyst saying yes, and the date, of course, not being expired. Otherwise, turn it on if you haven't done so. So the license must be enabled, in other words, before you can proceed with this example. So the geostatistical wizard is again, you went under the analysis tab and then geostatistical wizard. Once the extension is loaded, choose the inverse distance weighting and then the source data set, Overbrook aesthetics, and the field AVG index, which is the field name that contains that dimensionless index of aesthetics. And then you click next. And that brings us over to this next window here, which shows us in real time the surface, the interpolated surface. So we can try different things within the general properties to see how they change. So for example, a power of 2, and I change the maximum and minimum neighbors to be the same value as the number of points in the data set, 167, so that every point is used in the interpolation technique for each unknown location. And then when you click in here, you see this circle, and the center of that circle, there's a little crosshair right here. And when you click on that, it tells you what the estimate is over here. So you can click around and see what the estimated average index is based on the parameters you set up here. It also shows us what the weights are right down there. So when I click at that location where there is no observed value, then I have 167 weights, each that belong to one of the neighbors. And you can see the red one here, the dark red one, which the biggest influence is right there. So it has a 0.46, almost 50% influence on the value of where the crosshair is. And then the one that's colored light brown right here, that has a 0.09. You see how quickly these go down after we get to 1, 2, 3, 4, maybe around 10 or so. We're down to 0.019 influence in terms of the weight. So these points that are further away are having very little influence on the value to be estimated at that crosshair. And you can click around to check different values in different places. And one thing you'll notice here is what is called bullseying. Bullseying? Well, these are called bullseyes anyway. I don't know if there's a process called bullseying or not, but here's a bullseye. And you can see a bullseye basically look like this around known locations. You get something that looks kind of like that, because around the known locations, the estimated values, if there's no other points around that location that are fairly close, just around it will all be very close to the value that is observed at the center. So again, these are all the regular lattice points where we're estimating. They'll have values that closely match that location right there in all directions, because obviously the weight is high. Their values are highly influenced by the value closest, which is one location. Like that. So you see bullseyes around a lot of the single location things, or complex bullseyes here to make kind of islands of things. So these three values are kind of somewhat similar. And so their bullseyes kind of merge together in this particular space. And this is a normal thing to see with inverse distance weighting, is this bullseye effect. And that's, again, because of the rapid decay in weights that you have with increasing distance, which means any isolated points that are somewhat spatially isolated will have estimated values around them that are very similar to them and only them. Now, assessing how good this particular model is is done through what's called leave one out cross-validation, which I kind of quickly explained before. And we'll look at it again here. So leave one out cross-validation is simple to understand. If there's 167 points, right, in our data set, our observed data, we take n minus 1, which is 166 points, and we save, or we take note of the one we left out. So we take 1 point out of the 167, that leaves 166. That 166 is used to create a surface like that. And then from the 1 point that was left out of the creation of that inverse distance weighted field, we then extract the value from the field. Let's say it was right here. We extract the value right there, and that is then compared with the point that was left out, which is also right there, but it was never used in the creation of the surface, and we get a difference or error, which is what we see right here. So we have measured and then we have predicted, and 167 times a new one of these things right here was created, always using 166 points each time. So each row means that row was left out, or that point was left out when the surface was created, and then the measured value was recorded for that point because it's one of the data points, and then the predicted one at that same location is taken, and then the difference is shown here as the error. And this is a way in which errors, one of the many ways in which errors can be determined when you're doing interpolation. So this is called the leave one out cross-validation method. Now, these errors then are summarized in a root mean squared error right here. You'll see how that's summed to do that in a second. So the root mean squared error is in the units of the input. So it's in the units of the input data set. And it's that what we're kind of interested in seeing. We're also interested in seeing if there are any large errors. And you see the plot here is the predicted, and the observed is right there. So it's observed versus predicted. And this is just a scatter plot with a trend line in blue and a one-to-one line in light black there. And this just is a means of exploring how close the measured and predicted are. If you had a perfect model, in that every time you leave a point out, that the predicted value for that point that you left out is exact same as what the measured value was, you would have all your points lining up along this one-to-one line right here. And that just means that a predicted value is equal to a observed. Okay, in reality that never happens, so you get this scatter that you see in here, variability, which is hopefully random variability. And if it is random variability, then your model is good, or it's fit properly, and you could then use it as a means by which to have an interpolated data set. In our case here, it certainly doesn't look like this inverse distance weighted model is optimal, for sure not, because you can see that if you look at just along the blue line here, you can see that there's, in this region of the plot, there's hardly any points, but there's a lot down here, which means the predicted value is overestimating compared to the observed. So this is the region of overestimate. So that's an overestimate region. And then up here, likewise, we have hardly any values below that trend line. And that means that we have, fewer, we have underestimation here, in that we have larger values observed than we do predicted, because they're all in this region over here instead of over here. So that's overprediction, or underprediction, I should say. So underprediction, because each of these points is just a error value right here. And well, so it's the distance from the point to the blue line is the error, basically, or point from, well, not really in this case, but it's measured versus predicted. And so they're not obviously here one-to-one, and it doesn't look like it's a very good model because we have a lot of over and under prediction. If we had an equal amount everywhere around that blue line, let's say, then it would probably be pretty good. Or you can even compare it not to the blue line, but if you wanted to, even more so just to the one-to-one line right there, which would be a perfect prediction. Well, this area, we have higher values of prediction than we have of observed. So we're overestimating, and of course here, underestimating. And that's how we can assess that particular type of a model. So then we might go back and try some other things, see if maybe optimizing the weight, or something like that, the exponent might help with that, till we get something that is a good model. But this one is not a particularly good one. But the difference between a not particularly good one and a very good one for inverse distance weighting is not that big of a difference. It's not going to really change the overall macro patterns that you see on the right-hand side. Details change, but the macro pattern doesn't change too much. So that root mean squared error, again, is done by summing the squared error terms divided by n to the square root, or to the power of 5, which is the same as a square root, right? And that's your root mean squared error. And that's always in the units of your input data. In this case, it's a dimensionless value because it's a dimensionless, but it's in index units. So 0.419, for example, means that the uncertainty here, the root mean squared error, could be, for a lot of the points around 0.4 aesthetics units away from the true value, let's say the observed value. So that's one of the things you can. That's about the only thing you can really get that's useful from in terms of assessing the fit of a model like this one, or many spatial models, just the RMSE, root mean squared error. And you want that to be as close to 0 as possible. And you have to decide beforehand, usually beforehand. So before doing the interpolation or anything, what type of an RMSE value you would be comfortable with for presenting or giving that data to somebody, or using it in as part of a process in a model, for example.